So we'll see if that's any better. That should be there. Well, we'll see. Okay, so for those watching the video, we just did a sample quiz, which I'll post on Canvas. And we'll go over the answers after the break, just to evaluate how you're feeling. I guess general sense, you feel like that was good, bad? One of them, the units were a little tricky, I think. Okay, and then there was some stuff we haven't actually done, just quick questions like Shockley quasar, photoelectric. Okay. So this is the PDF that's posted. So for those watching the video, it's kind of hard to see, but you have the PDF. So I introduced the parallel plate capacitor, which I believe most of you are familiar with. So I want to go over how this is practically used as a storage device. So capacitors can be used to store charge. So you can either polarize it like it's shown here. The top is net positive, so we've depleted the metal of its electrons. The bottom is net negative, so we've actually put extra electrons into that metal. And we'll talk more about electrons and metals later in the course. And then they're separated by an insulating medium and a gap of D. So the general formula for capacitance is C equals epsilon A over D. So here's another one of these tricky things where the notation is important. So they've put epsilon as the absolute value, and then they've shown it instead as K epsilon naught. So again, epsilon naught is the permittivity of a vacuum, or the permittivity of free space. Now I introduced, and so what they've just done is epsilon by itself. Some would call the absolute value. And what they've put as K here, I said was the relative. So when I write things, I'll try to stick to this notation. But when you read textbooks or diagrams or Wikipedia or whatever, you know, they'll use different notations. So that K epsilon naught is the exact same as the epsilon R. It's just a different way of writing it. So we store energy by accumulating charges on two closely separated pieces of metal. They're separated by an insulating medium, which we also call a dielectric. And because you have charges that want to be together, but they can't get together, right? They're not able to get through. So it has to be energy. We could calculate a potential electric energy by saying there's this much charge and this much distance, and we could put it into our UE general formula. Q1 would be the charge on the top plate, Q2 is the charge on the bottom plate, R would be this distance D. But we can simplify it, and people have done the work to define this value of capacitance. So let me tell you what the units are, because it's going to get a little bit funky between voltage, capacitance, charge, and energy. Okay. Plus, capacitance has a parameter of capital C, which is not to be confused with the unit coulomb. Okay. It's just the way it is, unfortunately. So capacitance is defined as charge, which I'll use a capital Q, per voltage. I'll put a delta, okay? And the units we'll use, I'll use square brackets to try and show, I mean, these are parameters and these are units. So it's often called a farad, named after Michael Faraday, the British scientist. So the unit is the farad. But a more simple SI way of thinking of it is coulombs per volt. Okay? So that means if I have a capacitor and it's rated to so many nanofarads. That's usually how they come if you buy them, nano or microfarads or whatever. I know if I put a voltage of 10 volts, well then I just multiply voltage by capacitance to say it will store this much charge. So capacitance equals charge per voltage. So it's a very practical value. And so here's an old school one you could build yourself where the dielectric medium is air. Of course, these plates have to be held very firmly in place because they want to pull together. Here's more what you would buy for circuitry if you're building Randall circuits or whatever. And there's lots of different types, and it's blurry, but you can read it hopefully. And so what do these types refer to? It's telling you what that dielectric medium is that's separating the two parallel plates. So it can be as simple as paper. It can be this tantalum electrolyte, fancy stuff that someone's made. Polyester and polycarbonate are types of plastics. And then there's fancy engineered ones, which is more of an electrical engineering question, how they do that. Silver mica. Mica is a mineral. It's a layered mineral. Okay, so let's go through.
Excuse me.
Yes, question.
Are you live streaming?
Hmm?
Are you live streaming? The class, are you live streaming?
It's not live, no, it's a recording. Yeah. Okay. So there's some example questions. I think, well, let's do 141 because it's so easy, hopefully. 2-point charges. So we'll go back to electrostatics, and then I'll do this example of capacitors. And I'll leave this if you want to do it by yourself. Okay. So 2-point charges each have a charge of 1 coulomb, or 2 meters apart. If the distance between them is doubled, by what factor does the force between them change? Okay. Does anyone know? Yeah?
4.
Factor of 4. So why?
Because it's squared. The force is squared.
It's an inverse square law. Right. So if there's a question like this, you could calculate the force. You have the information you need. You could calculate the force at both and then figure out the difference, and that would be acceptable. But if there's an easier shortcut way, like saying, well, it's an inverse square law, force is proportional to 1 over r squared. So if the distance doubles, that ratio is going to be a factor of 4. That's fine, as long as it's clear what your logic is. So force is proportional. So some people for proportional will write like sort of an alpha fish looking thing. Maybe you've learned some other way of writing it. That's fine as long as it's clear. 1 over r squared. I mean, you could sort of, I think it's logically simple enough if you just say, therefore, if r doubles, force is divided by 4. That would be okay. You could also explicitly write out like F1, F2, divide them, and show your math. As long as your logic is clear and it shows you understand the principles, you're going to be fine for marks and things. I just want to make sure you understand it. Okay? Yeah, and if it is a bit confusing, it is sometimes safe to say F2 over F1 is proportional to, well, it is equal to, 1 over R2 and you can just substitute this in, and I guarantee you will get the right answer, okay? So that's the sort of math way of doing it, and you don't have to calculate the actual force in newtons, but you can. Okay. So let's do this example. I might. Let's see. Well, time-wise. Let's solve that after the break, actually. And instead what I'll do is I'll show you the stuff on the PowerPoint. So I'm not raising and lowering this thing over and over, okay? So we'll solve that after the break. Oh, come on. So I want to show you this thing called the Ragone plot. It's named after this professor. I think he was at Case Western University, which is an American school. And he was trying to find ways of comparing different types of batteries, like nickel, cadmium, lead acid. So lead acid is the kind you have in gas-powered cars. Nickel cadmium is an older, like cell phone or mobile phone in the house, replaced by a nickel metal hydride, and now, of course, lithium ion. He said, well, how do I compare all these different things? And they came up with, or he came up with, plotting power density versus energy density, okay? So, yeah, so we'll come back and solve a problem. It'll just take a little while, okay? So, power of energy. So we use the watt. And a watt is just joules per second, okay? But this isn't power and energy I've plotted, it's density. So what does that mean, okay? So I could also call this the specific energy and the specific power, which is a bit of an older nomenclature. You'll often see it for things like specific heat capacity. You might have learned that in chemistry, okay? What I mean is, it's how much energy do I get per mass. So a very important concept in energy storage is going to be how much energy you get per kilogram of your whatever, say it's a battery. I could also plot this versus volume, where I say it doesn't matter how heavy it is, but how big is it? That's going to be important for a car, right? Like you think of the Model 3 or the Nissan Leaf or whatever. They want the car to be a certain size, and it can be heavier or lighter. It can only be this big. But on the other hand, if I'm making a cell phone battery, well, maybe the size isn't as important. Actually, the battery is a very small component here, but I don't want it to be heavy, right? We like nice light phones. But the traditional Ragone plot is against weight. The other thing to note is it's a logarithmic plot. So every line is going up a factor of 10. So this allows us to easily compare very different devices and different applications. So you'll often get them like this. I mean, these lines are not real. They've just sort of approximately here. They probably looked up a few examples that were kind of like around there-ish, and they made a square. But we can now very easily see, if I want a lot of power, the batteries aren't nearly as good as our capacitor. But when we come back to our example in a moment, you'll see the capacitor holds very little energy, right? So I can deliver energy quickly, but I don't have much of it. So this is the difference between driving up a hill versus driving all the way to Oslo, right? Assuming that was flat, which it's not, but whatever, fine. Driving around the Netherlands 400 times, because that is very flat. So the capacitor will get you up the hill really fast, but then it's done. That's all it does. You have to recharge it before you can do anything. Battery is more, I can go a long way, but it's not going to have nearly that. Well, it obviously can get you up a hill, because people do. but it's not going to have the power for really high power applications. For example, the flash on your phone is not using the battery. It will charge a capacitor, and it will use that to deliver the flash. With modern LEDs, it's slightly different, but historically, that's what it was. So if you have like the really old school phones, you'd hold a button usually to charge something up, and then you'd flash. That was a capacitor charging. You would have a battery that charged the capacitor slowly, and then you release all the energy all at once to make a really bright light, okay? So power and energy are important, so make sure you're very comfortable with watts, joules per second. But then also the idea that I can divide it by mass. Oh, that is awful K. Wow. Okay. All right, so does that make sense? I'll show you another example. If you go to research talks and things, it's like 80% of them start with one of these graphs. Okay. So here's another example, and this is just comparing batteries. So I've zoomed way in. I'm not looking at nearly the orders of magnitude I was. That before was, oh, I want a battery or a capacitor. And here is, which battery do I want? So primary lithium, so that's like those little coin cells you use once and it's gone. You have to buy a new one, those little CR button cell things. They hold a pretty good amount of energy. They're not terrible for power, actually, okay? They obviously have the disadvantage you can't reuse them, which this graph doesn't show. This graph also doesn't show how toxic it is, it doesn't show how expensive it is, it doesn't show the volume, as I mentioned. So there's a lot of things this doesn't show. But this person has added in this extra thing where they've estimated about how long, at that power and this energy, how long this battery is going to last. And so you can see these primary lithium batteries, 100 hours. But we use them for things like watches, right? Or people will have, you know, those dog collars with the invisible fence. They'll often have like a primary lithium like this because it will last weeks or months even. You just run it way down here, okay? Whereas a lead acid battery, well, you can get pretty good charge out of it, but 10 hours, then you need to recharge it. Well, if you're using it to start a car, that's fine, because you're going to run it up here somewhere and say it only needs to run for 40 seconds. Well, how long does it take to start a car? 5 seconds? 10? Okay, so these graphs are useful. Make sure you have a look at it and try to understand what it's telling you. And then it's also good to try and understand where this comes from, which is really just, well, I've drawn all over it, but if I have joules per second and I have energy and time, you just solve for time. Okay, so they've just done energy divided by power to estimate the time, okay? Does that make sense? All right, I think that's the end of this. Yeah, so try to be very comfortable going from joules to watt hour, coulombs to amp hour, capacity, well, we'll do that capacity question right after the break. But energy versus density. So specific energy, that's like the mass density. Technically, you can say massic energy, but I've never heard a native English speaker say that in my life. I've only heard French people say it because it works in French. So I don't know what Norwegian does, but anyway, but volumetric, specific means divided by the mass, and then absolute, which is just the real amount, okay? And then finally, capacity is referring to a charge in coulombs or in amp hours. Capacitance is referring to a capacitor, which has units of farads, which we just said was coulombs per volt. Okay? All right, any questions? If not, I'll grab those, I'll have a look, and then we'll have a break for 10, 15 minutes. We'll finish that question, and then I'm going to introduce you to lattices. See how far we get. Okay.